Welcome to this explainer brought to you by Forge College. Today, we are taking your smart wallet and putting it through the absolute ultimate engineering stress test. You know, if you've been following our applied Solidity development track, and specifically the Designing Smart Wallet Patterns module, we just wrapped up mapping our deployment protocols to criteria for our integrated smart wallet project. We've built something genuinely great. But now it's time to try and mathematically destroy it before a hacker beats us to it. We are transitioning your code from, hey, look, it works, to mathematically sound, highly secure, and cheap to run. So let's get started.
Here is our master inspection checklist. First, we'll go from blueprint to inspection. Then, we'll hunt for bugs with automated scanners. Third, we'll tackle the notorious reentrancy trap. Fourth, we'll shave off those excess gas costs. And finally, we'll pull it all together into the ultimate debug report.
Section 1. From blueprint to inspection. Let's see how we shift gears from merely verifying behavior to actively hardening our code.
Up to this point, our main question was basically just, does this wallet do what it's supposed to do? But now that mindset has to completely flip. We have to ask, how can an attacker break what we just built? We're going to treat this codebase like a newly invented, highly volatile machine. We aren't just blindly turning wrenches hoping things tighten up. Instead, we're following a tight, four-step blueprint: threat model, scan, fix, and validate. This loop keeps all our security and performance trade-offs explicitly clear.
So what does this actually look like? Well, it absolutely must start with threat modeling. Think of it like checking the architectural schematics to figure out exactly who has the privilege to push the buttons on our machine. For literally every external-facing function in your wallet, you need to list out the privileges, the external calls, and the state changes. You are mapping out the exact surface area that is exposed to the wild, wild west of Web3.
Moving on to Section 2, hunting bugs with scanners. Now that we know where our weak points are, we grab our diagnostic tools and start the bug hunt.
Thankfully, we don't do this manually. We let the machines do the heavy lifting. Static and symbolic analyzers like Slither and Mithril are basically automated magnifying glasses. They scan every single gear and pipe for microscopic fractures. And the crazy part is, they don't even need to execute or turn your smart contract on to test it. They simply read the raw logic and mathematically hunt for known vulnerability patterns that our human eyes would totally gloss over.
By simply running a script, like scan.sh, we let these automated tools compile a massive report of every squeaky hinge or loose bolt. In a professional workflow, you'll export these results into a structured format, like a JSON file. That way, you can easily track, filter, and eventually squash every single flag the system raises.
And man, the system will throw a lot at you, so we triage these findings rigorously. Critical means your wallet might spontaneously disassemble itself and burst into flames. High is a logic error just ripe for exploitation. Medium could be some nasty information leakage. And low, well, that just means we need a little oil on the gears for style or efficiency. Pro tip, always put out the big fires first.
Which brings us to Section 3, fixing the reentrancy trap. This is a notoriously dangerous flaw that scanners catch all the time. If you are building Web3 applications, you absolutely must understand this concept. For those completely new to this, a reentrancy attack is basically like a thief running up to an ATM and repeatedly asking for $100 way faster than the machine's computer can update the ledger. The attacker interrupts the contract midway through its execution and forces it to start over, draining funds because the contract hasn't even realized that the first withdrawal happened yet. Wild, right?
The fix is actually deceptively simple, and it all comes down to order of operations. A vulnerable contract recklessly hands over the cash before doing the math. The patched version safely deducts the balance internally first and only then sends out the transaction. Changing that order from send money, then update balance, to update balance, then send money is literally the cornerstone of safe Solidity development.
To make sure we never mess this up, we strictly adhere to the Checks Effects Interactions Pattern, or CEI. It's a foolproof way to guarantee our internal ledger is completely safe before reaching out to the outside world. You check the requirements, you apply the effects to your internal state, and only as the absolute last step do you interact with an external address.
But wait, there's more. We can actually weld a literal padlock onto the function by using a no-reentrant modifier. This physically blocks reentry loops using a simple private Boolean that flips to locked while the function runs. Even if an attacker somehow tries to loop back in, bam, the door is slammed shut. Access denied.
Section 4, shaving off gas costs. With the critical security holes successfully patched, it's time to check our fuel efficiency. Because in the world of smart contracts, clunky, inefficient code literally costs you and your users real money every single time it runs. We can implement targeted micro-optimizations without having to refactor the whole system. Simple habits like using the standard uint 256 consistently, packing your storage variables together, explicitly marking non-mutating functions as view or pure, and swapping clunky loops for efficient direct mappings. This tells the network your code is lightweight, which drops those transaction fees significantly.
To put that into perspective, look at this. We saw a massive 13.5% drop in gas consumption for our withdraw function after applying just a few of these tweaks. We went from over 85,000 gas down to under 74,000. When you multiply that by thousands of users making transactions, those micro-optimizations compound into incredible savings.
But listen to me on this one. As any good engineer knows, you absolutely must run regression tests. You use tools like an ETH gas reporter to objectively prove your fancy optimizations didn't accidentally break existing features. It is so tempting to keep tweaking code to save a few pennies. But if your newly optimized smart wallet fails its basic unit tests, congratulations, you've just built a highly efficient broken machine.
Almost at the finish line. Section 5, the final debug report. We need to gather all this evidence into one ultimate inspection artifact.
This is where we bring everything we've done into a clear, professional document. You don't just say, hey, I fixed a bug. No way. Your debug report must meticulously document every single finding. You log the exact file, the line number, the reproduction steps, the suggested remediations, and a direct link to the code commit that actually neutralized the threat.
And the standards here are sky high. A passing grade for integration means absolutely zero failing unit tests and zero unresolved critical or high-severity findings. We have a strict threshold. You just cannot proceed to the final capstone assembly if your automated scanners are still flashing red for logic errors. It's a hard stop. This kind of rigorous documentation is exactly what separates the weekend hobbyists from the professional engineers. Creating this technical record proves to everyone that your code isn't just working by accident or sheer luck. It's working because you systematically designed it, aggressively audited it, and optimized it to absolute perfection. So, with all that said, the puzzle pieces are locked down. The code is highly efficient and thoroughly documented. We've successfully audited and heavily optimized this smart wallet, leaving us with one final question. Are you ready to assemble the capstone and launch this thing into the real world? To master that final integration step and really dive deeper into advanced Web3 engineering, make sure you visit forge.college. Exploring the programs there is absolutely the best way to elevate your skills from writing basic code to deploying resilient, production-ready systems. Thanks for tuning into this explainer by Forge College, but before you go, ask yourself one final thing. If your most recent smart contract went live tonight, would it survive a hacker's midnight audit? Think about it. See you in the next one.